So now comes a very a long-standing tradition at the Fysica meeting. One of the plenary talks is always devoted to the Nobel Prize in Physics, which in 2014 was awarded for the invention of efficient blue LEDs. In the Dutch Journal of Physics, or shortly NTVN, some of you might have already read the contribution on LEDs by Maria Antonietta Lowy and Jan Anton Koster. And today we are very happy to have one of the authors of this paper, Jan Anton Koster, introducing the science and the impact of these beautiful blue LEDs. Jan Anton studied in Groningen, but also has some interesting links with the Eindhoven University. He got his PhD in Groningen with Paul Blom, a former physics student at TUA, and then spent several years at University of Cambridge, followed by a couple of years working in the group of René Janssen, again here in Eindhoven. Now Jan Anton is back where he came from. He has a position in Groningen in the group Photophysics and Optoelectronics at the Zernike Institute, and we are all looking forward to your talk, Jan Koster. The stage is yours. Let's welcome the speaker.
All right, thank you. Thank you for the kind introduction and the opportunity to be here today. What I'd like to do today is talk about the Nobel Prize in Physics that was awarded last year for the invention of blue light-emitting diodes. And this is going to be a non-specialist talk, so I'll start with a fairly long introduction about the importance of lighting, some background in semiconductor physics, and then I'll introduce the basic operation of light-emitting diodes and how to get white light from LEDs, and hopefully one of the light bulb that was just handed over to Professor Verlinde is one of these LED lamps, and especially definitely one here. All of them are used for white light, and of course there's a very interesting application, and there's something I'd like to mention about how to get white light. And then I'll go into the achievements by the laureates. So there will be an introduction before we can really appreciate what the laureates have actually achieved. So lighting is crucial in our society. For example, it's crucial in economic development, and this is something I never really appreciated, I guess. To me, lighting is sort of a luxury item, I thought. At home, you know, you invest quite a lot of money in nice-looking lighting if you're into that sort of thing, and they actually can be quite expensive, so it feels like a luxury. It's not, because it's very important for economic development, and that can be really appreciated, for example, if you're trying to study in the evening to improve your future prospects. And because lighting is so important, we actually spend a lot of energy on lighting. So about 20% of all the electricity that is generated is used up by lighting globally. So this is sort of the equivalent of all the energy that is generated by nuclear power plants. Now, light-emitting diodes can actually save quite a bit of this energy. So if we all switch to LED-based light bulbs, then we can save up to 40% of energy in total. In your home application, that might be even more. So I don't know if you've ever bought one of these LED lamps in the supermarket or in a hardware store, but they're actually quite expensive. And but the good thing is that they save so much energy that their payback time, if you will, if you compare a 40-watt incandescent light bulb, so the traditional one with an LED one, the payback time is about 1.5 years. So after 1.5 years of normal usage, you will have saved back the extra outlay in purchasing that LED lamp. And of course, this would be useless if they wouldn't last very long, but the lifetime is claimed to be about 20 years. I'm not so sure about the number, but it's definitely long enough to more than make up for the extra outlay. So this is sort of a schematic drawing of a light-emitting diode. So what we have here, we have several components, but at the heart we have a diode. So this is the thing that we will be talking about today, and this is a junction, a PN junction, typically a little bit more complicated, but at its essence a PN junction between two differently doped semiconductors. Now it's important to note that there are other very important components. For example, this light extraction dome here is very important to actually get the light out once it's generated. So this is, without this thing here, it will be a lot less efficient. So most of the light will simply be stuck inside the diode because of waveguide effects. So how do we get light from a semiconductor? So what we use in an LED are semiconductors. Semiconductors, of course, sort of in terms of conductivity, fall in between metals, which conduct very well, and insulators are typically plastics that hardly conduct at all. And there are several examples. Silicon, for example, is a well-known semiconductor, of course, so germanium, gallium nitride. And what we have here is if we have electricity flowing, that means that we have movement of electrons and holes in these materials. Now, what we have in an LED, how we get light, is by a phenomenon called luminescence. And this is different from what we have in an incandescent light bulb. In an incandescent light bulb, you heat up a filament by passing a large current, and because it's hot, it will start to radiate simple black body radiation. Now, this is not luminescence. Luminescence is actually defined as the emission of light for any reason other than a rise in its temperature. And essentially, this is a decay of an excited state. So that means that we put energy into the material, we excite it, and the loss of this excitation means that the energy has to go somewhere, and this is what yields, or can yield, light emission. And electroluminescence, that is the type of luminescence that we have in a light-emitting diode. That means that we create that excited state by supplying electrical energy. So we pass a current, we apply a voltage, we excite the material, and this excitation disappears by radiating light, hopefully, if things go well. So just a recap on a band diagram. So this is a typical diagram that we draw if we want to discuss a semiconductor. So on the vertical axis is electron energy, and then we have a valence band where all the electrons are immobile essentially, and we have a conduction band where we can have electrons flowing around. And now there's an energy difference between these bands, the band gap, and that means that there are states where no electron, or energies where no electron states are possible. That's this state. And now that is actually, that means of course that we have very little conductivity in the semiconductor at room temperature, but we can also use the fact that we have this band gap to create this excitation and to generate light. And that is what is depicted here. So we can have an electron in this conduction band, a hole in the valence band, and if those two meet, they recombine, and that means that the excitation is lost, and that means that we can get light emission. All right, so this is a different way at looking semiconductors. This is known as the bond model, so this is much more pictorial. So what we have here, and this is silicon as an example, is silicon atoms nicely forming bonds with their neighboring silicon atoms, and they do this because silicon has 4 electrons in its outer shell, and it wants to form bonds with neighboring silicon atoms and thus form a crystal. So and that is denoted by these lines here. They denote electrons. Now what can happen is that one of these electrons becomes free just by thermal energy, for example, and can move around in the semiconductor. And what that can also happen, what is left behind is known as a hole, so that is the place where an electron used to be. So now in its natural state, in its intrinsic state, there are very few free charges, so we have very little conductivity. And of course that's not very useful immediately if you want to make an LED. So what you can do to get more charges is a process called doping. And doping is a tremendously important process in semiconductor industry, and you can understand how this works. So here again there's silicon, and now the electrons are the black dots here, nicely shared between the silicon atoms. And if we replace one of these silicon atoms by, for example, by phosphorus, then we can get doping. And this is something you can understand if this is a cutout from the periodic table of the elements. So here is silicon, and here is phosphorus. Phosphorus is 1 to the right, so that means we have 1 extra electron in the outer shell. So if we replace silicon with a phosphorus atom, we have 1 extra electron here. So that means that we can have a free electron, so we can get conductivity. And we call this n-type doping because the free carrier is negative. And we also have P-type doping, where we replace, for example, silicon with boron atoms, so it's one to the left and one up. And then we get a free-floating positive charge. So now we can make semiconductors conducting. We can also make junctions, so and this is a drawing of what happens in such a junction, and that simply means that we take a slab of N-type material and a slab of P-type material, and we make a junction between the two. And what happens at this interface is that holes from the p-dope region start to diffuse into the N-type region, because we have many holes here, and very few holes in the N-type material, and electrons flow the opposite way. So here we get this, in this junction, we get a buildup of space charge. And this type of junction is what you can use to make a light-emitting diode. So this is how this sort of works. So this is without a voltage applied. Here we have the holes. These are the electrons. Here we have extra electrons in the N-type material. And if we now apply a voltage, then we start to inject electrons in the N-type and holes into the P-type, and they can move to this junction. And here the extra injected electrons will meet some of the holes, recombine, we lose that excitation, and we get light emission. And this is how you can get light from a light-emitting diode. Now, I've promised something about lighting, so that means that we also need to talk about colors. And this is the chromaticity diagram, and it displays all the colors that the human eye can see. As a function of a y and an x coordinate. What we have here is all the monochromatic pure colors, that is, around the perimeter, and in the middle we have all the colors that can be obtained by mixing. So for example, if you want to get white light, it makes sense to, or you need actually to combine different colors in order to get this thing here. And now if we put different semiconducting materials into this picture, and what is important to realize, of course, is that different semiconductors will have different band gaps, and different band gaps will yield different colors of light, and that's very nicely shown here. So this is a list of different semiconducting materials and the corresponding light-emitting diodes. And what you see is that the light that an LED gives is pretty close to a monochromatic color. Actually, its width is about 10 nanometers in the visible range. So that means if you want to get white light, so close to this thing here, you would need to make a combination of light-emitting diodes, right? There is you cannot use one single pure semiconductor, the tricks that you can play, to get white light. Now, the way you do this, if you want to get something close to this, you can combine, for example, 3 light-emitting diodes, because all the stuff that is within the triangle that I'm trying to indicate here can be obtained by a linear combination of these 3 light-emitting diodes of different colors. So to get white, you need a combination. And of course, there are different ways of doing this, and these are just some of the approaches. For example, you can combine a blue and a yellow light-emitting diode, or if you want to get better color quality, you can use 3 or even 4 different light-emitting diodes to get a nicer looking shade of white with a higher color rendering index. And of course, whether that's important depends on your application. If your application is signage, for example, or street lights, then the quality of the color is not so important. If you talk about lighting in your home or in your office, it's very important that the light actually resembles normal sunlight. And that is where this approach can be less attractive than using more light-emitting diodes. What you can also do is combine a blue light-emitting diode with a phosphor. So what happens here is that the phosphor absorbs that blue light and re-emits it at lower energies, so in this case, in the yellow part of the spectrum. And the overall result would be white light. So what is obvious here is whatever you do, you always need blue. You always need that blue component in order to get white light. And now if you look back in the history of light-emitting diodes, it actually goes back over a century ago, this is now over a century ago. So in the late 19th century, there was a process developed for making silicon carbide, also known as carborundum, and carborundum is still a very well-known abrasive that you can find in grindstones, but you can also use it for electroluminescence. And this was shown in the early 20th century by Round. So he demonstrated electroluminescence from silicon carbide. And there was a young Russian guy with very little formal training, Alyek Losev, who actually happened to invent the light-emitting diode in the 20s and 30s. And unfortunately, his invention was lost, and he died during the Second World War in the siege of St. Petersburg. But there was tremendous interest, and there were, and there still are, many people working in the field of light-emitting diodes, and especially in the 50s and 60s, it was realized that you can make red and green light-emitting diodes by using gallium phosphide as the operative semiconductor. And of course, many people tried to make blue LEDs because it was very quickly realized that white light would be tremendously attractive. And many tried to do this, but failed. And there's a problem with just the practicality of making a blue light-emitting diode. So first, gallium nitride was tried as a semiconductor. It has a suitable band gap of just over 3 electron volts. So that means that you can, and this emission will be in the blue or the UV part of the spectrum. So it is, in principle, a suitable semiconductor. But there are a couple of problems if you then want to apply it in a light-emitting diode. Now, firstly, it was difficult to control the doping. So just by the defects that happen to occur in this material, it tends to be N-type doped. So then to get P-type doping made the material very brittle. So that is a problem, of course, if you want to use the material in a PN junction. And also the quality of the crystals turned out to be very poor because of a mismatch with the commonly used substrates. So this was tried by many people, and at some point it was dismissed in favor of other semiconductors, so not gallium nitride. So enter the laureates. So these 3 gentlemen, Akasaki, Amano, and Nakamura, decided to stick to gallium nitride, and they actually solved these problems one by one. So first, and I'd like to go over some of their results. So in 1986, Akasaki and Amano published a paper, here's the reference in Applied Physics Letters, where they made the world's first high-quality gallium nitride layers. So what they did is they introduced a buffer layer of aluminium nitride that they first deposited on the substrate, sapphire substrate, aluminium nitride layer, and then the gallium nitride. And this, they actually made a list before trying aluminium nitride of a number of suitable components that could be used as a buffer layer, so sort of in terms of physical properties, lattice constants, for example, in between gallium nitride and sapphire, and aluminium nitride was the first one they tried, and this happened to work, and they stuck with it. So there was I'm not going to say that's luck, because they're obviously very clever researchers. But they used this, and it worked very well. And there's a picture here. So this is a crystal grown without this buffer layer. You can sort of see the dislocations and cracks in this film, and it has a poor mobility and very weak luminescence. And this is, so of course the gallium nitride layer itself will be transparent. There's a high band gap. So that is what you see in this picture. You don't see it. The fact that you don't see the crystal means that is high quality and nicely crystalline. And this has a much better luminescence and electroluminescence and electron mobility. This is the setup that they used. So they used a metal organic vapor vase epitaxy to grow this crystal. So the way it works is you have a chamber and a substrate. You heat the substrate, and you add precursors of the gallium and the nitride component, and they react on the substrate, and then you get a gallium nitride layer. And it's interesting to note that all these papers are in APL and Japanese Journal of Applied Physics and Journal of Applied Physics, and maybe that's a consolation to some, that if your paper does not get accepted in Science and Nature, that you might still have a chance of at some point, perhaps, who knows. So they publish more of these papers. Actually, so that was one problem solved, right? The crystal quality. Now they switched to the P-type doping. So in 1989, they published a paper where they successfully demonstrated this p-type doping, and they doped it with magnesium. Now, this was tried before, so that is not I guess the critical component of that paper. But what they found is that they needed to activate the magnesium by using low energy electron beam radiation. And then they made the first real PN junction-based LED. And this is a picture of, out of the substrate, you can see there's one blue light-emitting diode working. Of course, a tremendous achievement. So, and this is a cross-section of what they did. So here we have a sapphire substrate, followed by this aluminium nitride buffer layer, then undoped. So that means in this case that it's actually n-doped gallium nitride. And then a layer of magnesium-doped gallium nitride, where this part here that is shaded was treated with the low-energy electron beam to make a p-doped. You add an electrode, and voila, you have a light-emitting diode. Now, Nakamura also decided to work on this, and he built his own new reactor, and he made a number of important changes to the way that the doping and the crystal growth was being implemented that made it much easier to make this on a larger scale. So this is a diagram from his 1991 paper showing his setup. So he has a substrate, and he actually has two inlets for the gas flow. So what he, and it's also shown here on the left, he has a main flow that carries the trimethyl gallium and the ammonium components of gallium nitride, if you will. And he found that he needed a subflow to gently push the reactants onto the substrate to make the growth happen. And this, he claims, is very important. Without that second flow, he did not get a nicely continuous film. He got small islands of gallium nitride. And he found that he didn't need this aluminium nitride buffer layer. What he did is first, on the substrate, deposit a layer of gallium nitride at relatively low temperature, and then increase the temperature of the substrate, and then he could grow high-quality gallium nitride on top of this. So that's an easy way to implement. And he also found another way of activating the dopants. So again, he used p-type doping of gallium nitride by doping it with magnesium. But he found that if you simply heat up the substrate, this removes the hydrogen that forms a complex with magnesium, and thereby activates the doping. So this activation of the doping that Akasaki and Amano also found was not understood at the time. So he figured out what was actually going on. And 1 year later, so in 1993, Nichia Chemicals, the company where Nakamura worked at the time, started producing blue light-emitting diodes. So this is a slide of further developments, although it's actually technically not correct because this stops at sort of 10 years ago. But this is shows the development of blue and other light-emitting diodes. So all three laureates then contributed to the making these devices more efficient. For example, focusing more on indium gallium nitride and improving the device structure using double heterostructures and quantum well structures, and inventing the blue laser diode. So you can see here, this is a graph of performance in lumens per watt versus year, with the red and the yellow light-emitting diodes. Already, well, it's even before the Axis starts, so it's well beyond, or in the 50s and 60s it's already happened. And here you can see the rise of the nitrides and the blue light-emitting diodes. So it's a very steep increase in performance. What I also like about this graph is that they show a slightly different approach. It's this line, the molecular solids and the polymers. So these are also light-emitting diodes. They're a little bit different. And I just want to spend one slide on this, since we're in Eindhoven today, and Philips here in Eindhoven played a large role in the development of this type of device, and that is not using inorganic semiconductors like gallium nitride, but using organic semiconductors to basically make very similar devices. There are physical differences, but many of the main principles are the same. And this here is a lab-scale device where we have a beautiful white light coming off a substrate, and this is a picture from product by Philips, the Lumi blade, where we have these very thin panels, 0.7 millimeters, if I'm not mistaken, of a light-emitting diode that emit. So the whole surface here is light-emitting diode that emits this beautiful shade of white light. So in this, I'd like to summarize is that and just to remind you that the Nobel Prize is awarded not for well, I know some students at our university said, wow, this is not science and this is engineering, but actually if you look at and I don't agree with them in the first place, but anyway, and if you look at the will, it says that the prize goes to those who've conferred the greatest benefit on mankind, and I think that is absolutely the case here, as this is a tremendously useful invention. And they were awarded this invention for a new energy-efficient and environmental-friendly light source, the blue light-emitting diode, which completes the red, the green, and the blue triangle of LEDs. And with this, I'd like to thank you.
Thank you very much for this beautiful overview.